Hey everybody, and welcome to another episode of Space Science with Python. Before we start, I would like to wish everybody a happy new year. I hope you had a great time, great Christmas days, and also a nice party last night. So I hope some of you will watch this video on the 1st of January. If not, of course, some want to maybe relax and not start learning on the very first day of January. But for those of you who would like to directly dive into space science, this is now the second last video of our NEO project. And today we are going to compute some probability density functions of our NEO model that we introduced last time, the Grundvik model. But before we start, I would like to mention that I added two notebooks in today's session, 13.1 and 13.2. 13.1 is just a notebook that enriches our Grundvik model a little bit more with the state vectors and also apparent magnitudes. And I would like to mention that in the Grundvik model in notebook number 12, we used, I think, a mean anomaly distance of, 10 degrees. I reduced it to 60 degrees or increased it so that we reduced the number of NEOs because, well, I only have on this computer only 8 GB of RAM, and yeah, that was quite difficult to get results in a suitable amount of time. So if you like to work with more NEOs, please change the values in notebook number 12 accordingly, but I think this is still sufficient. So you need to execute notebook number 12 and 13.1 to get the new Parquet file called enriched Grundvik model with apparent magnitudes. So let's skip this one here and let's dive directly into notebook 13.2. It is, again, I just created some sections to work on this data. So before we go a little bit too much into detail, let's maybe load our data, set up our matplotlib routines, and load also the the Parquet file, and also converting the longitude values for our matplotlib sky projection, because the longitude values, they are not defined from 0 to 2 pi, they are defined from -pi to pi, so we have to do some math magic. Now today we want to create a kernel density estimation of our NEOs in the night sky. So why do we want to do this? Well, last time we did our on our sky notebooks, we created some scatter plots to see where the NEOs are, but we would like to have some more data scientific function that describes our night sky, like for example the number of NEOs or the probabilities of finding NEOs, let's say in the steradian, or let's say in a square degree field in the sky. The square degree field is not in the SI units, but we will work with these square degrees because I think this is a little bit more intuitive than saying, well, the unit sphere is has a size or an area of 4 pi or something like that. So we will work in square degrees today. First of all, I would say we use our Grundvik model here in cell number 5, and we ignore all NEOs that are too close to the sun. So we only consider NEOs that are at least 45 degrees away from the sun. And I would also suggest to only take a look at the brighter NEOs. So let's say NEOs that are brighter than 25 meg. Additionally, we extract also the latitude and longitude values, because these values are then later used for our kernel density estimation. You will see, wait a second, we use the latitude and the longitude values. Why not longitude, latitude? This is more intuitive. Well, this order, we will take a look later in a cell where we work on the kernel density estimation. This has a certain reason, so to speak. This takes a little bit some time. So here we can also take a look at the number of NEOs, and you see that we have around 19,000 NEOs, or only 19,300.5, so that's quite strange. Well, please note that we enriched our NEO model, yeah, with a factor of 6, yeah, with the by increasing the mean anomaly. We do some filtering, so it's of course it's possible that we get some odd number of NEOs, and we have to divide it by 6 to get the same scale as the Grundvik model provides us, because we increased the Grundvik model by a factor of 6. So yeah, this is, let's say, our unbiased number of NEOs, but yeah, not the number we will work on. But yeah, you will see just in a moment. For our plot in cell number 7, we need also to add the sun position. So we use SPICE to compute the the position of the sun as seen from the Earth. So here with the SPICE function SPK GPS. And then we compute also the opposition direction, so 180 degrees away from the sun. Now in cell number 8, we can simply create now our first scatter plot with all NEOs. And you have seen this picture before in, I think, video number 8 and 9. Our sky map of ecliptic longitudes and latitudes in degrees, and here is the sun. This is the area that is not observable, and here is our opposition field. And you see, well, is there some opposition effect? Do we have more NEOs than in the background noise? You could guess it, but let's use kernel density estimation to determine whether this works or not. So whether the opposition effect has an effect or not. So this is the topic of the next section here in cell number 9. We introduce now scikit-learn's neighbor submodule, and we have here the kernel density. And it's very important to mention now that we use a certain metric called the Haversine metric. So this is like the, let's say, the Euclidean metric you use on a sphere, right? So we cannot use the Euclidean or Manhattan metric. You have to use the Haversine metric on the sky projection. And the Haversine metric is implemented in such a way, so here's also the link to the scikit-learn documentation, that it requires first the latitude and then the longitude. So that's the reason why we have latitude, longitude first. And the bandwidth, well, I set it artificially to 5 degrees to smooth out our distribution. And as a kernel, I use now also here the exponential function. So there are certain distributions, also kernels, that are quite sufficient for map projections, like the one we can derive from the von Mises-Fischer distribution. I don't know if I pronounce this correctly. And well, but these kind of distributions, also the corresponding kernels, they are not implemented in scikit-learn. So I was thinking, well, let's use something that is quite easy to understand and applicable, and this is in our case just like the exponential function. So we have now here our KDE, so our kernel density estimator, and now in cell number 10, when we set our mesh grid, yeah, you see here in latitude and longitude coordinates, we can now compute the score here in this line, and the score is given in, it provides logarithmic results, so we have to convert it using the exponential function, so that at the end we get our probability density function of the NEOs in the sky. Now this is only half the truth. We have to convert it now to get a suitable density estimation, because now we have like some number, right? Some probability density function, but we would like to have something that says, okay, I don't know, XYZ NEOs per square degree. So how do we have to handle this? We have to take the probability density function. So you see this here in cell number 11. So this cell is still computing. We have to multiply it with the number of all NEOs that we have. Yeah, so the length of the list that contains all coordinates. We have to convert it from the radians domain to the degree domain by applying 180 divided by pi squared. And then do not forget that our NEO model is enriched by a factor of 6. So we have to divide at the end of the day also by 6. And this is what we do here, so that at the end of the day we get our NEO density function. And this is what we will do in this very last cell number 11. But before we can run this, we have to wait until the kernel density estimation is computed. So I would suggest to wait for a few seconds and let's see what the results are. You see now cell number 10 is executed. So this took like around a minute or so on my computer. So now we can execute cell number 11, where we create our kernel density Sky Map. And maybe you get an idea now why I don't create an interactive map. So this is also the outlook and summary I will mention in a second. It takes a lot of time, so let's stay with the hard-coded way. So what we do here is now we create a contour plot, we add some color bar and so on, and also adding the sun again to get the final kernel density estimation of our NEO model. And what you see here is quite interesting. We see here now the sun, we see here the opposition direction, and you see based on the KDE, so on the kernel density estimator, that the number of the density or the probability to find an NEO in this region is a little bit higher compared to, let's say, the background. Yeah, so you see here far away from the opposition, it's the probability decreases. So you see here the color bar, it goes down from yellow to green. And so here at the opposition, we have like around 1 NEO per square degree that we can observe. But most objects are observable, I would say, here at this region, some degrees away from the sun, to the left and to the right, or west and east respectively. Yeah, so now you have a nice tool where you can adjust here in cell number, where was it? Here in cell number 5, you can adjust the apparent magnitude, you can adjust the angular distance to the sun. You can also filter for different eccentricities or orbital elements in general. You can also compute the NEO class and so on. And with this tool, as a scientist or as an observer, you could now create your personal probability density functions to determine, okay, you would like to observe, let's say, armors with a certain eccentricity range. Where should I look at? Yeah, and okay, mostly it is around the ecliptic plane, but then you get really actual results. And if we now have some computation, some observation power and would observe it, we could then verify or deny our model, how we created this. So this is quite interesting to see how these figures evolve for different settings. But as you see, this is a multi-dimensional problem. What's the outlook now? So I said this is the second last video. Our last video next time will introduce telescope properties and settings. So we will set up something like a telescope, the aperture, we will set some properties for a CCD camera and so on, so that we get this kind of plot for a telescope with a certain camera. And then you have a very multi-dimensional tool you can adjust for your own personal needs and telescope. And then you can start observing and see whether this tool here and the model can be verified by your observations or not. Of course, you have to add something more, like for example, the atmospheric attenuation and so on. But this is like, let's say, a rough estimate how many NEOs you would observe. Very last thing, you've seen that the computation takes some time. So creating an interactive tool using IPy widgets would be, this would take some time. So if you have a more powerful computer or you would like to run this in the cloud, feel free to do it, so you can adjust these things accordingly. Or what you could also do is you can compute the density functions for a predefined set of parameters and values, and then you can create some interactive widget where you have some predefined parameters there where a user can adjust the settings. I hope you learned something. I hope you will continue learning in this new year 2023. We will start the new year with ending a project from last year, but I hope you learned a lot, and I hope you will stay tuned to the next video, and then let's see how we will proceed with our tutorial series. Thanks for watching, and see you next time.